All right, good morning or afternoon, whatever time you're watching this. This is Miss Gallant. I'm going to be leading y'all through lesson 2.4 in solving equations. Make sure you have the right paper before you get started. It's got the little lobster on it. And we are solving more complex equations, and we're looking at different numbers of solutions with equations. Yes, equations can have more than one solution or no solution at all, and we're going to look at that today. All right, so I'm going to leave you to go through your learning targets and all that. Just make sure you've got the right paper. And the first question is, what is the definition of solution? I think everybody's pretty much got that. They know that, okay, solution means answer. But there's really more to it than that. So I'm going to go ahead. Well, I was going to say pause the video, but really and truly, let me just go ahead and lead you through this one. In order for a value to be a solution to the equation, it has to make the equation true. So a solution is any value that, when substituted into an equation, makes the equation a true statement. Okay, so if you need to pause the video and write it down, you can. Just one more time, that's a solution is any value that, when substituted into an equation, makes the equation a true statement. Okay, so we're just going to investigate what that looks like. So I've given you 3 different equations, and I've given you a list of numbers. So I'm going to jot these numbers down here. So I've given you a list of numbers, and we want to know if any of these numbers are solutions to any of these equations. So how could I play with it? How could I figure that out? Well, what I can do is, and I'm going to do this in 2 colors because for me that visually makes sense. I'm going to substitute the number in for x. I ran out of room. I must have written too big. Okay, so I'm going to substitute that number in for x, and then I can use my handy dandy calculator and see if that yields a true statement. So when I do that, I'm going to do 9 times 1/2, which is 4.5, plus 5 equals, and then 1/2 plus 2 is, actually it might be easy. You know what, this one's going to be easier to distribute. So we'll do 4 times 1/2 is 2. 4 times 2 is 8. And half of 5 is 2.5. Okay, so 4.5 plus 5 is 9.5. Equals 2 plus 8 is 10, plus 2.5 is 12.5. Okay, so I plugged 1/2 in. It did not yield a true statement. So I know that 1/2 is not a solution to this equation. And notice I did the one with the fraction for you because I'm so super nice. We're going to do the same thing here. This time I'm going to write a little bit smaller, so I didn't think that through this first time. So again, we're going to plug 1/2 in for x. And then we're going to simplify and just see if it yields a true statement. So half of 7 times 1/2 is 3.5, minus 10 equals half of 3 is 1.5, plus 14. Okay, I don't even need to finish this out to tell you this isn't going to be true, because 3.5 minus 10 will give you a negative number, 1.5 plus 14 will give you a positive number, so this is not going to yield a true statement. And then we'll do the last one. We have 3 times 1/2 minus 12 is equal to 3 times 1/2 plus 1 minus 15. Okay, so if I do 3 times half, that is 1.5 minus 12 is equal to 1.5 plus 3 minus 15. Okay, so let's, and if I subtract, let's see, where's my calculator? If I can pull it up on my phone. Okay, so we're going to do 1.5 minus 12, which gives me negative 10.5. Oops. And then 1.5 plus 3 minus 15 is also negative 10.5. So this one yields a true statement. So this, so 1/2 is a solution to this equation. Okay, I know you guys do not want to see me work all of these out. I have full confidence that you don't need me to work all of these out for you. It is plug in, simplify, plug in, simplify. So if you'd like, you can pause the video and do the rest on your own. I'm, however, going to skip this. Feel free to pause it and complete it. I'm going to skip this and move on, but you are welcome to check your answers with the key that should be posted on the course calendar for this class. Okay, so number 3 asks, how did you approach the problems above? Is there another way to approach them? So if you started doing these, you probably noticed that plugging each and every one of these numbers in took a really, really long time. So what you could do is start solving the equation. That is another way to approach it. So this is another one that you need to answer. Did you just simply plug in every single number? Or did you solve it and see if you noticed any patterns? So is there another way to approach them? There is. You can solve the equation yourself. I'm going to leave this for you to answer though, because I don't know how you approach the problems after I did this one. I'm not psychic. All right, so we're going to go on to the next page. And number 4, again, I can't answer this one for you because it's what did you notice about the problems above? What do you wonder about the problems above? If you put nothing or don't write anything, that is not an acceptable answer. I need to see something written here. So make sure that you have something that you notice about. You had to have noticed something eventually. It could be none of those numbers worked, or all of those numbers worked, or something. You had to notice something. Okay. All right, so let's move on. So let's move on to the meat and potatoes of this. All right, an equation can have no solution. There is no solution if there is no value of the variable that will create a true mathematical statement. An equation has infinitely many solutions if there are unlimited number of values that will create a true statement. Okay, so number 5, Mary, Laura, and Carrie solved the following 3 equations as shown with an N. I apologize for that. Identify each of the equations as having one solution, no solution, or infinitely many solutions. So if we look at this, we remember an equation has no solution if it cannot yield a true statement, and infinitely many if it can always yield a true statement. So if we look at Mary's equation, so let's look at what she did. First, she distributed this 3, which is good. Here she combined like terms. And then if you look, we have 3x plus 2 equals 3x plus 2. She subtracted the negative 3 from each side and got 2 equals 2. This is a true statement. So if you think about it, we canceled out that negative 3x. So does it matter what x equaled? If x equaled 0, we would still end up with 2 equals 2. If x equaled 50, we would still end up with 2 equals 2. If x equaled 4,537, we still get 2 equals 2. So it does not matter what I plug into x. It could be negative. It could be a fraction. It could be 0. No matter what, we get a true statement. So since I can substitute every single value that I can come up with in my head and it be true, we're going to say that this has infinitely many solutions. Okay. All right, let's take Laura. So Laura had a little more complicated of an equation. Let's look at what she did. So if you look, she took this negative and distributed the negative. You can do that. You can take the negative. If we're making this entire quantity negative, which is what that means when you have the negative on the outside parentheses, you can just take that and change the sign of everything inside the parentheses. Easier math. Okay, so now we have this negative 5x and negative 4x. When you combine them, that gives you a negative 9x. All right, so we have this negative 9x minus 3 equals 8 plus 6x. We added the 9x to each side. Negative 3 equals 8 plus 15x. We subtracted the negative 8 from each side. Got negative 11 equals 15x. Divided each side by 15. Got x equals negative 11 over 15. So this, even though it's a fraction, don't panic, but this looks more like what we're used to. We get x on one side of the equation and the numerical value on the other side of the equation. So when we see something like, we have the solution, we have what x equals. So we're going to assume that this is a true statement. All of her math was correct. It's a true statement. We have that x equals 11 over 15. So we have what x equals. That would be one solution. So, yeah. It's what we're used to seeing. So that makes us feel better. It's kind of comfortable. We know what that looks like. All right, let's take a look at Carrie's equation. We're going to distribute this 2. That gives us 8x plus 6 minus 3x. Equals 17 plus 5x. All right, so Carrie then combined like terms and got 5x plus 6 equals 17 plus 5x. We subtracted the 5x from each side and ended up with 6 equals 17. Is that a true statement? No, no matter what x is, 6 and 17 will never be equal. If I say you earned $17 for mowing my lawn and only pay you $6, you're going to be pretty mad at me. They're not equal. It's not the same thing. So here, this is not true. It does not matter what I plug in for x because those are going to end up canceling anyway. So since it doesn't matter what I put in for x, if I put 0 in for x, 6 and 17 still won't be equal. If I put 50 in, 6 and 17 will not be equal. So since nothing I put in will make this a true statement, this has no solution. Okay, I hope that makes sense. All right, so number 6 says, take a look at the third step in each problem. What conclusions can you draw here? So if you look, I did box the third step. I bet people are wondering, what's she doing? I boxed them for a reason because I knew this question was coming up. All right, so let's look at Mary's. If you look here, we have 3x plus 2 equals 3x plus 2. So Mary's looks the same on each side and had infinitely many solutions. Okay, what about Laura? Let's look at her equation. We have negative 9x minus 3 equals 8 plus 6x. Every number is completely different. So Laura's numbers are completely different. And she had one solution. All right, then we get to Carrie. So in this step, she has 5x plus 6 equals 17 plus 5x. What do you notice about the x's? Well, the x's has the same coefficient, but different constants. So the x's have the same, or are the same, but what we're adding is different. So carries we can say the number in front of x is the same. Rest is different. And we had no solution. Okay. So that's just something to notice in all three problems. We're going to come back to this and make a nice, pretty, how can I tell without solving way of looking at these. Okay. So this will be important on the, probably on the next page. All right. So number 7, determine the solutions to each of the following equations. So I'm going to ask you to pause the video. Now you have been solving equations for a while, so you shouldn't need me. I'm going to ask you to pause the video and try these on your own. Okay, so here I have all three solved for you. So let's look at number 8. So double check first that make sure you got the same things that I got. And let's look at 8. So 8 asks, how many solutions does the first problem above have? I got z equals 0. So I know some people are going to say, well, z equals 0, that there's no solutions. But remember, a solution means any number that makes the problem true. And 0 is a number. So what this means is that if I plug the number 0 in, this will make a true statement. So if I put 0 in for z, 6 times 0 is 0, 30 times 0 is 0, and you're left with 12 on either side, which is a true statement. And if I plugged in any other number, this wouldn't work. So z equals 0 is a solution. So this is one solution. This is one solution. The solution is 0, and 0 is the only value that makes the equation, true. Okay, number 9. Which of the following equations has no solutions? And which one has all real numbers or infinitely many solutions? Explain your reasoning. Okay, so if I look, the second one has 4 equals 4. It yields a true statement. 4 equals 4 will always be true. So this middle one, the second one, has all real numbers or infinitely many solutions. Number 2 has infinitely many solutions. Okay, so how do I know that? Well, I end up with a 4 equals 4. Now let's look at this again. Let's look at this again. I ended up with the exact same thing on both sides of the equations. So we're going to write here, yields an always true statement. Okay. Number 3, if we look, we end up with 3 equals 7. That is never true. So 3 has no solution. When simplified, it yields an always false statement. When we simplify, we're going to get something like 3 equals 7 every single time, and we know that can never be true. Okay, if you need to jot down notes, feel free to pause the video or rewind or whatever you need to do to be successful. I'm going to go ahead and go on to the next page. Oh, goodness. I just realized that number 9 goes with this question. I was wondering why. So if we're looking at this without solving it, which one do you think would yield infinitely many solutions, and which one do you think has no solution? So if you would, go ahead and pause the video and make your assumptions. Okay, hopefully you got that the first one would have no solution, and the second one would have infinitely many solutions. And the easiest way to do this is if you were to cross out the x terms, and once it's simplified like this, if you were to cross out the x terms, you're going to get a 5 and then nothing. Or 5 equals 0. That's not true. If I were to cross out my variables here, I'm going to get negative 2 equals negative 2. Now, before you just start crossing off variables, remember, they have to be the same. I have 3x and 3x. They'll cancel themselves out. That's why I'm crossing them out. And maybe that was... maybe I went too fast on that. But when I start solving it and I subtract my 3x, they'll cancel and I'll have 5 equals 0. So not true. When I cancel these out, I'll have negative 2 equals negative 2. Also not true. So something we want to do is we don't want to have to solve these out every single time. Now, when we looked at the ones we did earlier, you find that page, like with Mary, Laura, and Carrie, we did have to do some simplifying. But really, if we get to the third step, we can tell how many solutions they're going to have. And we're going to use the terms coefficient and constant to explain that. So remember, a coefficient is the numeric factor of the term. The other way to look at it is it's the number in front of your variable. So in 2x, the coefficient is 2. The constant term is a term that only contains a number. So like this is when we have at the end like plus 4 or something. So if I have 2x plus 4, 2 is the coefficient, 4 is the constant. X is not the coefficient, x is the variable. So I can actually take that out since I wrote the expression up here. All right, so what did we notice about the coefficients when it had no solution? Well, the coefficients were the same. So the coefficients are the same. But what about the constants? Well, if I'm adding 5 here and adding something completely different over here, they will never be equal. So we're going to say coefficients are the same, constants are different. Okay, what about one solution? Well, when we were looking at one solution, not only were the, well, actually, let me go back to that. Okay, so on the ones that had one solution, so Laura's, if we look at her coefficients, they were different. So were their constants. But if we look here, we had different coefficients and the same constant, and we got 0 when that happened. So, but it's still one solution because 0 can be a solution. So in order to have one solution, the coefficients must be different. And that will give you one solution every single time. Now, if the coefficients are different and the constants are the same, your solution will always be 0. But if the coefficients and constants are different, then you'll have a different number as your one solution. And then infinitely many solutions. So again, when we go to infinitely many, the coefficients were the same, But what do we notice about the constants? So coefficients are the same. Now the constants, if we look, they're both -2. They're the same as well. So are the constants. I don't know why I drew a line. So are the constants. Okay, so if nothing else, number 10 is going to save you a lot of heartache trying to solve some equations. If you recognize that pattern, if you recognize that, oh my goodness, the coefficients are the same, so I don't have to go much further. Let me just see if these are going to be infinitely many or or no solution. So that's going to help you recognize that pattern and not panic when you start seeing that, oh my gosh, I'm not getting a solution. I shouldn't get a solution. Okay, so I am going to stop the video here. It's been almost 30 minutes. I didn't mean for it to be this long. I was hoping it would be a little more quick. I'm going to ask that you continue task 2 and 3 on your own. Task 2, it does say discussion groups. So if you have friends that are also taking this class and y'all would like to discuss these over email or Google Hangouts or text message, however, go for it. Like, I would love it if y'all were able to talk to each other outside of class about these. That's my dream. And then task 3 is just creating your own equations. And I think it'll be pretty interesting. I'm looking forward to seeing what everyone comes up with. So thank you so much for paying attention to this and for taking good notes. Feel free to rewind or go back and view whatever you need to over and over again. If you have any questions, send us an email, and I hope you guys have a great day.